Hello, welcome to the video for Chapter 3, Section 2. This section introduces some formulas that may start to feel a little tricky. Just realize you can't be lazy with these types of problems. They're going to force you to think through them. And yes, some of them will have multiple steps. Most of these formulas require you to decide something about the problem first, so you have to do a little bit of work before you sub information into the formula. Just take it step by step, figuring out which direction you need to go and applying what you've learned to each part of the journey of that problem. You can do it. I have faith in you. Okay, let's get started. Welcome to the video for Chapter 3, Section 2. We're going to dig into some probability formulas this section. Specifically, in this section, we're going to learn how to find the probability of an event given that another event has occurred. We're going to distinguish between independent and dependent events, and we're going to learn how to use the multiplication rule. Let's get going. Okay, before we build up to these formulas, I need to make sure we're all on the same page with something you need to fundamentally understand if you're going to do well in this section. That is, understanding what comprises a standard deck of cards. If you have managed to get this far in life and not played cards with someone, I hope that changes, as it can be really fun. But here's a breakdown of what's in the deck so you can confidently deal with all of these playing card questions. Okay, first of all, there are 52 cards total. There are 4 suits, or those little symbols that are on the cards. 2 of them are black and 2 are red. Clubs are black, spades are black, hearts are red, and diamonds are red. Okay, next, there are 13 cards per suit. What are those cards? They are the numbers 2 through 10. Notice there's not a 1. And what are called face cards: Jack, Queen, King, and Ace. Okay, what does this mean? Overall, what this means when you're dealing with numbers and drawing cards from a deck is that there are 4 of each type of card. For example, there are 4 aces, 4 threes, etc. And there are 2 of each color of each card. For example, there are 2 black aces, 2 red threes, etc. Okay, I hope that helped anybody who hasn't dealt with cards before. If you're one of those, make sure you took some notes about this so it'll help you when you're working on problems. It may seem basic to some of you, but I think a little review never hurts anyone. Okay, on to the work of this section. A logical starting question might be to ask, how do we find the probability of 2 things happening in a sequence? This type of question might come up in marketing or in medical research. To answer that question, we need to determine an event's conditional probability. A conditional probability is the probability of an event occurring given that another event has already occurred. The conditional probability of event B occurring given that event A has occurred is written like this. Notice the notation. P of B given that A. That straight line in between B and A is interpreted as the phrase given that, or just given. So we read this as the probability of B given A. Okay, here's an example. 2 cards are selected in sequence from a standard deck. Find the probability that the second card is a queen, given that the first card is a king. Assume that the king is not replaced in the deck. Well, because the first card drawn is a king does not affect whether we draw a queen the second time. But the fact that it does not get replaced does affect it, because it reduces the number of cards to choose from 52 to 51. That means our sample space has decreased by 1. But because the first one was a king, we know we still have 4 queens in the deck. So our numerator in our probability, 4, because there are 4 queens, is not affected by the previous action of drawing a king. So what does all of this mean? Our probability of event B, that the second card is a queen, given event A, that the first card is a king, is 4 over 51, or about 0.078. If we multiply that by 100%, we get that there is a 7.8% chance that those 2 events will happen in sequence. Okay, here's another example. The table shows the results of a survey in which 970 U.S. adults were asked whether they have ever ridden as a passenger in a self-driving vehicle. Find the probability that an adult is 18 to 64 years old, given that the adult has ridden as a passenger in a self-driving vehicle. Okay, so we're told that the people in question have been passengers in a self-driving vehicle. So we know that we're dealing with the 225 people in this category. That is event A. Next, we look at event B, that the person is 18 to 64 years old. So we look at this section here. So now we have our two numbers. The intersection of those two is 202, and then our denominator, or the total number, is 225. The probability of event B, a person being 18 to 64 years old, happening, given event A, that the person has been a passenger in a self-driving vehicle, is 202 over 225, or about 89.8%, or 0.898. And that makes sense intuitively if you look at the table. The majority of people who have ridden as passengers in a self-driving vehicle are the younger group. So reaching probability of a fairly high number, 89.8, seems reasonable. Okay, let's do another. Now, some probabilities are calculated based on the independence of the events in question. Two events are said to be independent when the occurrence of one of the events does not affect the probability of the occurrence of the second event. Events that are not independent are said to be dependent. Consider, for example, the probability experiment of rolling a fair six-sided die. The probability of rolling a 2 has nothing to do with whatever number was rolled previously. The outcomes that happen when you roll a die are independent of each other. It doesn't matter what was rolled previously. It does not affect the probability of getting a certain outcome on the next roll. We can show that events A and B are independent if we show that the probability of B, given that A has happened, is equal to just the probability of event B happening by itself. Another way to word it, if it helps you, is that we show the probability of the first thing happening, given the second thing has happened, is equal to the probability of it happening. Okay, if that was confusing, don't worry about it. Use what I said before in the formula. Showing either of these two qualities proves that the two events are independent. Let's break this down even further. If we calculate the probability of B, then we calculate the probability of that happening given something else has already occurred. Then we compare those two probabilities, and if the two probabilities are equal, the two events are independent. And if the two probabilities are not equal, the two events are dependent. Okay, let's look at an example. Decide whether the events are independent or dependent. Number 1, selecting a king, event A, from a standard deck of 52 playing cards, not replacing it, and then selecting a queen, event B, from the deck. Well, first we need to figure out what is the probability of the second event on its own. That would be the probability of just selecting a queen. Well, we know that there are 4 queens in a standard deck, so the probability of that happening is 4 out of 52. Then what's the conditional probability of drawing a king first and not replacing it? So from there we need to determine what's the probability of drawing a queen given that potentially the first card that was drawn was a king and it wasn't replaced. Well, we already kind of figured that one out. The probability of drawing a queen, given that we drew a card that was not replaced and that card was a king, was 4 out of 51. These two probabilities are not equal to each other. The probability of B compared to the probability of B given A are not the same fractions, so these events are dependent. Really, it comes down to this. You know two events are dependent if the sample space has been affected for that second trial. So in this case, the key wording was not replacing the first card, or not putting it back in the deck. That affected the sample space, or the number of cards in the deck we had to choose from for the second draw. Because we didn't replace that first card, we're no longer drawing from a deck of 52, we're now just working with 51. So your conditional probability is going to be different than the probability of just that event happening alone. Okay, let's do another one. Decide whether these events are independent or dependent. Tossing a coin and getting a heads, event A, and then rolling a fair six-sided die and getting a 6, or event B. Well, the probability of the second event, event B, without considering anything else, is just 1 out of 6, because there's only one way to roll a 6 out of possible 6 outcomes, so 1/6. And the conditional probability of first tossing a coin doesn't change what happens to the outcome of the die. So when we consider the conditional event of flipping that coin before we pick up the die and roll it, our probability isn't affected. The probability of rolling a 6, given that you picked up a coin and flipped heads, is just still 1 out of 6. Flipping that coin doesn't affect the sample space of rolling the die. So because these probabilities are the same, these events are independent. The occurrence of the first event does not change the probability of the second event. Now that we've figured out how to distinguish between independent and dependent events that occur in sequence, we now will apply what's called the multiplication rule. We'll use these formulas to find the probability based on whether we've determined that the events are independent or dependent of each other. The probability that two dependent events A and B will occur in sequence is the probability of A times the probability of B given that A has happened. This is again when we're saying the probability that A happens and then B happens. A and B are dependent events. Now, if we happen to know that events A and B are independent events, then the multiplication rule can actually be simplified to just the probability of the two events separately multiplied together. So the probability of independent events A and then B happening is the probability of A times the probability of B. These rules can be extended for any number of independent events. Okay, let's practice using the multiplication rule and the probability ideas from the previous section to complete the following problem. Two cards are selected without replacing the first card from a standard deck of 52 playing cards. Find the probability of selecting a king and then selecting a queen. We've actually done this problem in parts already. What we're doing now is finding the probability of them happening in sequence. We know that the first card is not replaced, so that means that these two events are dependent events. So by our formula, according to the multiplication rule, we multiply the probability of the first thing happening and then the second thing happening, given that the first thing happened already, which is a conditional probability. Okay, we figured out a little while ago that 4 out of 51 would be our conditional probability. So in total, the probability of selecting a king, not replacing the card, then selecting a queen is 4 over 52 times 4 over 51, which was the probability of getting a queen given that we already drew a king. So 4 over 52 times 4 over 51 gives us 16 over 2652, or about 0.006. Okay, let's try another one. A coin is tossed and a die is rolled. Find the probability of tossing a heads and then rolling a 6. Again, this is a situation we've seen before. The outcome of the coin is not affecting whether or not we roll something with the die. So we already said that these were independent events. But now we're not just determining each event, we're finding the probability of them happening in sequence. Before, we were just finding the probability of each one. Okay, so the probability of tossing a heads is 1 over 2, or 1/2. And since these are independent events, the multiplication rule says to just multiply the probability of the second event, which is 1 out of 6, the probability of rolling a 6, by the 1/2. So now we multiply 1/2 and 1/6, and we get 1/12, or about 0.083. The likelihood of these events happening in sequence is about 8.3%. Okay, we're going to do 3 more problems that will really hit home how to pay attention to the wording of the problem when you're solving them. The first one says, for a particular knee surgery, the probability that the surgery is successful is 0.95. Find the probability that 3 knee surgeries are successful. Okay, so a few things to notice here. The probability of 1 surgery being successful is 0.95. The chance for success for 1 surgery does not affect the chance for another to be successful. So another thing to note is these are independent events. Now that we know that they're independent, we can use the rule to simply multiply the probability of 1 success, 0.95, by itself 3 times, so that we have 0.95 times 0.95 times 0.95. This gives us about 0.857. Okay, let's try another one. For a particular knee surgery, the probability that the surgery is successful is 0.95. That's just like before, but here's our new question. Find the probability that none of the 3 knee surgeries are successful. Okay, so we know that the chance for success for 1 is 0.95, but we need to find the probability of it not being successful. So to me, that sounds like we need to use the complement rule. So we need to subtract the 0.95 from 1 to get the chance of a failure, which is 0.05. Okay, so now we have one part of it. Now we have found out the probability of failure for 1 surgery, which is 0.05. Because these events are still independent of each other, we multiply this amount by itself 3 times. So 0.05 times 0.05 times 0.05, and we get 0.0001. Okay, last one. This one is a little different than what we've seen before. It says, find the probability that at least one of the 3 knee surgeries is successful. So at least one means one or more. The complement to the event at least one successful is the event none are successful, because at least one could mean 1 is successful, or 2 are successful, or 3 are successful, but it does not mean none are successful. So this is another case where knowing the complement rule is handy. We figured out in the last question how to find the probability if all 3 were failures. That would be our first step if this question was by itself. Then we would use the complement rule and subtract that result, which was 0.0001 from 1. That gives us 0.999. So the probability that at least one of the 3 knee surgeries is successful is 0.999. Now let's think about if you were starting this problem from scratch. Another way you could write the formula would be 1 minus the probability that the event is not successful raised to the power of the number of trials, or times the experiment is performed, in this case 3. So we would have 1 minus 0.05 raised to the 3rd power, which results in the same answer, about 0.999. Okay, here's a little bit of a review of the probability formulas we've covered recently. If you want to pause the video and get a screenshot of these formulas, or just make sure you understand where they're located in your notes, you can do that now. You can also find this handout with formulas we'll be going over in the next section as well, under Chapter 3 Prep Files. It is simply called Probability Formulas Handout and has 2 pages, which you can print 2-sided if you want. Okay, we've figured out how to distinguish whether 2 events are independent or dependent. The kind of probability formulas that use these types of events we call AND probability. You're finding the probability that one event happened and another event happened in sequence. The trick for these is to make sure you understand whether one event is going to affect the outcome of the other, then to use the correct formula. If the events are independent, meaning the first event does not affect the outcome of the second, you simply multiply the probabilities of each together. If, on the other hand, the events are dependent of each other, meaning the occurrence of event A affects event B, then you need to find the probability of event B happening given that event A happened. Then multiply that result with the probability of event A happening. Okay, then we have the at least once rule. This will be obvious because the question will ask you the probability of something happening at least once. This one has a slightly different type of formula. You need to find out the probability of event A not happening first. Then raise it, or multiply it by itself, to the nth power, or that many times. Then you subtract that result from 1. Okay, I know that's a lot to digest, but I know you'll get the hang of it. That's it for this section. I'll see you in the next video.